Werner Heisenberg's journey into the world of physics and his pivotal role in the development of quantum mechanics stands as one of the most profound contributions in the history of science. Born in 1901, Heisenberg was one of the brightest minds of his generation, deeply influenced by the revolutionary changes that were taking place in physics during the early 20th century. In a period dominated by classical physics, which had largely been shaped by the works of Newton and Einstein, Heisenberg's contributions would challenge and reshape the very foundations of how we understood the physical world. Heisenberg's path into quantum mechanics began at a time when physics was undergoing a profound transformation. By the early 1900s, the old deterministic laws of classical mechanics, formulated by Isaac Newton, had been shaken by a series of discoveries. The classical idea that the universe was predictable where, if we knew the current state of any system, we could predict its future was challenged by new phenomena that classical physics could not explain. Experiments with blackbody radiation, the photoelectric effect, and the behavior of electrons in atoms led to the development of a new theory, quantum mechanics. At the forefront of this revolution were figures such as Albert Einstein, Max Planck, and Niels Bohr. While Einstein's work on the photoelectric effect and Planck's quantum hypothesis were crucial steps toward the birth of quantum theory, it was Heisenberg's involvement that would solidify his place in the pantheon of great scientific minds. In 1925, Heisenberg, still a young scientist, developed the mathematical framework for what would become known as matrix mechanics, a groundbreaking theory that would become one of the cornerstones of quantum mechanics. His work focused on understanding atomic and subatomic systems in ways that were radically different from the classical models. In contrast to classical physics, which treated particles as discrete objects, Heisenberg's approach viewed particles as governed by probabilities. This shift marked the beginning of a new way of thinking about the behavior of matter. Instead of being able to precisely predict the trajectory and location of a particle at any given moment, Heisenberg's theory showed that we could only describe the probabilities of where a particle might be found. This approach required new mathematical tools and concepts, particularly the use of matrices, abstract mathematical structures that represented the possible states of a system. Heisenberg's ideas were groundbreaking, but they did not come without controversy. The idea that nature, at its most fundamental level, was probabilistic rather than deterministic was a significant departure from the classical worldview that had dominated scientific thought for centuries. This shift in perspective was not only a challenge to the scientific community, but it also deeply impacted the philosophical discussions of the time. The question of whether the universe was inherently predictable or whether uncertainty was a fundamental feature of nature became a central debate among scientists and philosophers alike. One of Heisenberg's most significant contributions came in 1927 with the formulation of what would become known as the Uncertainty Principle. This principle states that it is impossible to simultaneously measure both the position and momentum of a particle with absolute precision. The more precisely one of these quantities is known, the less precisely the other can be known. This principle was not simply a limitation of experimental tools or techniques, it was a fundamental property of nature itself. The uncertainty principle shattered the old idea of a deterministic universe, where, in theory, everything could be known and predicted if enough data were available. Instead, Heisenberg's uncertainty principle introduced a new, probabilistic model for understanding the microworld, where certain information could never be simultaneously precise. The implications of the uncertainty principle were profound. It suggested that at the quantum level, the very act of measuring one property of a system could disturb it in such a way that our knowledge of other properties was inevitably limited. This was a direct challenge to the classical idea of an objective reality that could be measured and understood without ambiguity. In classical mechanics, a scientist could theoretically measure the position and momentum of a ball in motion with great precision. However, at the quantum level, Heisenberg showed that the same degree of certainty was unattainable for subatomic particles like electrons. While the uncertainty principle itself was groundbreaking, it was also part of a broader philosophical shift in the scientific community. The probabilistic nature of quantum mechanics raised fundamental questions about the role of the observer in the physical world. In classical physics, the observer was a passive entity that simply measured the properties of the system without affecting it. However, in the quantum world, the observer played a more active role in shaping the outcome of experiments. The famous thought experiment known as Schrödinger's cat, proposed by fellow physicist Erwin Schrödinger, illustrated this point. It suggested that until an observation was made, a system could exist in multiple states simultaneously, existing as both alive and dead at the same time. This paradox underscored the strange and counterintuitive nature of the quantum world. For Heisenberg, the uncertainty principle was not just a mathematical tool, but a new way of thinking about reality itself. The idea that reality at its core was indeterminate, a universe of probabilities rather than certainties, was both liberating and unsettling. It challenged centuries of scientific thought, from Newtonian mechanics to the philosophies of determinism that had been closely tied to the rise of modern science. The uncertainty principle, along with the broader framework of quantum mechanics, forced a re-evaluation of the very nature of knowledge and existence. In addition to his work on the uncertainty principle, Heisenberg's contributions extended to the development of quantum mechanics as a whole. He was part of the team of scientists that worked on developing the theoretical framework of quantum mechanics alongside Bohr, Max Born, and others. Their collective work on the foundations of quantum theory led to the development of quantum field theory and the understanding of atomic structure. Heisenberg's matrix mechanics, Bohr's model of the atom, and Born's probabilistic interpretation of quantum mechanics all contributed to the creation of a unified theory of quantum mechanics, which would go on to be one of the most successful theories in the history of science. The role of Heisenberg in these developments cannot be overstated. His ability to think abstractly and his keen mathematical mind allowed him to create a framework that not only explained existing experimental data, but also predicted new phenomena that would later be confirmed through experimentation. His work on the atomic structure, in particular, helped refine our understanding of how atoms interact with light, leading to the development of quantum electrodynamics and the eventual discovery of the Higgs boson in the 21st century. Heisenberg's matrix mechanics also laid the groundwork for the development of quantum computers, which promised to revolutionize technology in the coming decades. Beyond his scientific contributions, Heisenberg's legacy is marked by the way he engaged with the philosophical and ethical questions raised by quantum mechanics. He was deeply concerned with the implications of his work for the way we understand the world and our place in it. The uncertainty principle, with its radical departure from the classical worldview, challenged not just the scientific community, but also the broader culture of the 20th century. For Heisenberg, science was not a purely objective endeavor. It was deeply intertwined with the way we think about reality, truth, and human knowledge. Through his work, Heisenberg reshaped our understanding of the physical world, but he also opened up new ways of thinking about the limits of human knowledge. His ideas challenged the assumption that science could ultimately provide a complete and deterministic description of the universe. Instead, Heisenberg introduced the idea that there are limits to what we can know about the world, and that these limits are built into the very fabric of nature. This philosophical shift was not easy for many to accept. It was met with resistance from some of Heisenberg's contemporaries, particularly those who were committed to a deterministic worldview. Albert Einstein, in particular, famously disagreed with Heisenberg's uncertainty principle. He believed that the universe was ultimately governed by laws that were predictable and precise, even if we had not yet discovered them. Heisenberg, however, maintained that the uncertainty principle was not a mere inconvenience or limitation, it was a reflection of the true nature of reality. Heisenberg's work on quantum mechanics was not just an academic exercise, it had real-world consequences. The development of nuclear technology, the rise of quantum computing, and the exploration of quantum entanglement all trace their roots to Heisenberg's theories. Heisenberg's legacy, therefore, extends far beyond the confines of theoretical physics. His work has shaped the technological landscape of the 20th and 21st centuries and continues to influence the fields of quantum mechanics, computing, and even philosophy. In the next part of this speech, we will continue to explore the wider implications of Heisenberg's legacy, his collaborations with other key figures in physics, and how his work set the stage for future breakthroughs in the world of quantum mechanics and beyond. Heisenberg did not merely change physics, he forever altered the way we think about the universe itself. Heisenberg's profound influence on quantum mechanics and his role in the broader scientific community cannot be overstated. His collaboration with other renowned physicists, particularly Niels Bohr and Max Born, marked the culmination of an era of intense intellectual exchange that would lay the foundation for modern physics. Their collective efforts led to the formulation of the principles of quantum mechanics, a theory that fundamentally changed the way we perceive the nature of reality. One of the most important aspects of Heisenberg's work was his development of matrix mechanics. Unlike Bohr's atomic model, which was based on the notion of discrete energy levels, Heisenberg's approach used a mathematical tool known as matrices to describe the behavior of quantum systems. This allowed Heisenberg to formulate a theory that could explain atomic behavior without relying on classical concepts such as particle trajectories. His matrix mechanics, while initially difficult to understand, proved to be remarkably successful in explaining experimental results and predicting new phenomena, making it one of the key pillars of quantum mechanics. Heisenberg's matrix mechanics also paved the way for later developments in the field of quantum field theory. This theory, which describes how fields interact with particles, forms the foundation for much of modern physics, from particle physics to the study of condensed matter. Quantum field theory has had profound implications, leading to the development of technologies such as semiconductors, lasers, and magnetic resonance imaging, MRI. These applications, which are now part of everyday life, are a testament to the lasting impact of Heisenberg's work. Despite the immediate success of his work, Heisenberg's contributions were not universally accepted without challenge. One of the most significant debates in physics during the early 20th century was the interpretation of quantum mechanics itself. While Heisenberg's matrix mechanics and the uncertainty principle revolutionized physics, they also brought up deep philosophical questions that scientists like Albert Einstein were not willing to accept. Einstein famously disagreed with Heisenberg, arguing that God does not play dice with the universe. Einstein's belief in an objective, deterministic universe stood in stark contrast to the probabilistic nature of quantum mechanics, which Heisenberg had helped to establish. The debate between Einstein and Heisenberg and other proponents of quantum theory culminated in what is now known as the Bohr-Einstein debates. These discussions, which were at times heated, centered on the very nature of reality. Einstein's position was that quantum mechanics, while successful in explaining experimental results, was incomplete. There had to be hidden variables that determined the behavior of particles. Heisenberg, along with Bohr, argued that the uncertainty principle was not merely a reflection of our inability to measure particles precisely, it was an intrinsic feature of nature itself. These debates, which lasted for decades, ultimately led to a deeper understanding of the limits of human knowledge and the philosophical implications of quantum mechanics. The importance of the uncertainty principle and its impact on the philosophy of science cannot be underestimated. It raised fundamental questions about the role of the observer in the measurement of reality. In classical mechanics, the observer had no effect on the system being measured. The state of the system was determined independently of the observation. However, in the quantum world, The act of measurement plays a critical role in determining the state of the system. This idea, known as the observer effect, further challenged the traditional notions of objectivity and determinism. It suggested that at the quantum level, the act of observation itself can influence the outcome of an experiment. This realization has far-reaching implications, not just for physics, but for our understanding of the nature of reality and the limits of human knowledge. Heisenberg's influence extended far beyond his contributions to quantum mechanics. He was also deeply involved in the broader philosophical and ethical questions raised by his work. Throughout his career, Heisenberg engaged with the idea that science was not merely a tool for understanding the physical world, but was also a deeply philosophical endeavor. Heisenberg recognized that the discoveries made by physicists had the potential to reshape our view of the universe and our place within it. This was especially evident during the period of World War II, when Heisenberg was involved in Germany's nuclear research program. While his work during this time remains controversial, it highlights the ethical dilemmas faced by scientists when their discoveries can be used for destructive purposes. Despite the ethical challenges Heisenberg faced during the war, his post-war career was marked by a commitment to fostering international scientific collaboration. After the war, Heisenberg became an advocate for scientific cooperation across national borders, recognizing that scientific progress could only be achieved through shared knowledge and collective effort. This commitment to internationalism was reflected in his role as the director of the Max Planck Institute for Physics, where he worked to rebuild the scientific community in Germany after the war. Heisenberg's legacy is not only defined by his scientific discoveries but also by the way he approached the relationship between science and philosophy. He was one of the first scientists to truly grapple with the implications of quantum mechanics for our understanding of the world. He understood that the uncertainty principle, while a powerful tool for understanding the physical world, also raised profound questions about the nature of knowledge itself. What can we truly know about the world around us? Can we ever achieve certainty in our understanding of reality? These questions, which Heisenberg explored throughout his life, remain central to both the philosophy of science and the study of quantum mechanics. In his later years, Heisenberg continued to write and speak about the philosophical implications of quantum mechanics, contributing to the ongoing debate about the interpretation of quantum theory. He published several books on the subject, in which he sought to explain the broader significance of his work. One of his most important contributions was his book Physics and Philosophy, in which he explored the relationship between the two fields and discussed the philosophical implications of quantum mechanics for our physics understanding of reality. In this work, Heisenberg argued that science and philosophy are not separate endeavors, but are deeply intertwined. The questions raised by quantum mechanics, he believed, were not just questions for physicists to answer, they were questions for humanity as a whole. Heisenberg's work has had lasting implications in both the scientific and philosophical communities. His uncertainty principle and his contributions to quantum mechanics continue to shape the study of physics today. The development of quantum computers, the study of quantum entanglement, and the ongoing search for a unified theory of quantum gravity all owe their foundations to Heisenberg's work. In addition, his philosophical writings continue to influence debates about the nature of reality and the limits of human knowledge. Heisenberg's legacy is a testament to the enduring power of science to challenge our understanding of the world and to inspire new ways of thinking about the universe. The man who made physics uncertain did more than just change the course of science. He reshaped the way we think about the world itself. Through his contributions to quantum mechanics, Heisenberg introduced a new paradigm in which uncertainty is not just a limitation of our measurements, but a fundamental feature of the universe. This paradigm shift has had far-reaching consequences, not only in physics, but also in the way we view the relationship between science, philosophy, and human knowledge. Heisenberg's legacy endures in the ongoing exploration of the quantum world and in the profound questions about reality that his work continues to raise. In the end, Heisenberg did not just make physics uncertain, he made it possible for us to see the universe in a completely new light. Werner Heisenberg's contributions to quantum mechanics were nothing short of revolutionary. He was at the heart of a scientific revolution that forever altered our understanding of the universe. Heisenberg's pioneering work led to the formulation of key principles in quantum mechanics, particularly the uncertainty principle, which challenged the deterministic view of the world that had dominated physics for centuries. As we delve into the second keynote, which focuses on Heisenberg's role in shaping the philosophy of science and its impact on the broader intellectual landscape, we see a figure whose influence extended beyond the equations and experiments. His work on quantum mechanics forced not just a scientific reevaluation, but also a philosophical one, reshaping the way humanity perceives knowledge and reality. In order to understand the broader significance of Heisenberg's contributions, we must first recognize the context in which his work emerged. Before Heisenberg and his contemporaries introduced quantum mechanics, the dominant scientific paradigm was rooted in classical physics, a deterministic framework largely defined by Newtonian mechanics. In this deterministic view, the universe was governed by fixed laws of nature. If one knew the position and velocity of every particle in the universe, one could predict the future with absolute certainty. This classical worldview provided a sense of order and predictability, which aligned with the philosophical ideas of rationalism that dominated the intellectual landscape for centuries. However, by the early 20th century, a series of experimental anomalies began to challenge the foundations of classical physics. The photoelectric effect, studied by Albert Einstein, showed that light could behave as both a particle and a wave, defying the classical wave theory of light. Similarly, Max Planck's work on blackbody radiation introduced the idea of quantization, suggesting that energy could only be emitted in discrete amounts, or quanta. These discoveries, along with others, signaled that classical physics could not fully explain the behavior of matter at the smallest scales. This marked the birth of quantum mechanics, a new framework for understanding the behavior of particles at the atomic and subatomic levels. Heisenberg's role in this revolution came when he developed matrix mechanics, a mathematical framework that helped describe the behavior of quantum systems. This approach was radically different from classical physics. Instead of describing particles with precise trajectories, Heisenberg's matrix mechanics treated particles as being governed by probabilities. Rather than specifying a precise path, Heisenberg's equations calculated the likelihood of a particle being found in a particular state. This departure from determinism was revolutionary, and it set the stage for what would become one of Heisenberg's most famous contributions, the uncertainty principle. The uncertainty principle, introduced by Heisenberg in 1927, is one of the cornerstones of quantum mechanics. It states that it is impossible to simultaneously measure both the position and momentum of a particle with arbitrary precision. The more precisely one of these properties is measured, the less precisely the other can be known. This principle was not a limitation of our measuring instruments, but rather a fundamental property of nature itself. At the quantum level, particles do not have definite positions and momenta in the way that classical physics envisioned. Instead, they exist in a state of probability, with a range of possible positions and momenta, but no single, fixed value. The implications of the uncertainty principle were profound. It challenged the very notion of determinism that had dominated scientific thought for centuries. In classical mechanics, if you knew the current state of a system, you could predict its future with certainty. However, the uncertainty principle suggested that at the quantum level, the future was not fully predictable. This idea upended centuries of philosophical and scientific thought. The deterministic view of the universe, so strongly associated with figures like Newton and Laplace, was no longer sufficient to describe the behavior of particles at the atomic level. For Heisenberg, The uncertainty principle was not merely a mathematical construct, it was a reflection of the true nature of the universe. Heisenberg's uncertainty principle introduced a fundamentally new view of reality. Rather than being a precise, predictable system, the universe at its smallest scales was probabilistic. The behavior of particles was governed by probabilities, not certainties. This idea had far-reaching implications, not only for physics but also for our broader philosophical understanding of the universe. If the future was not strictly determined, what did that mean for the nature of reality? Could we ever truly understand the universe, or was there always an inherent limit to what we could know? These questions resonated deeply within the scientific community and beyond. Heisenberg's uncertainty principle also had profound implications for the philosophy of science. Classical physics, with its deterministic laws, had provided a sense of objectivity. The scientific method based on observation, measurement, and prediction was grounded in the assumption that the universe was understandable and predictable. However, the uncertainty principle suggested that there were limits to human knowledge. It implied that science could not, and would not, provide a complete and deterministic picture of the universe. There were fundamental uncertainties built into nature itself. This realization had far-reaching implications for the way scientists viewed their role in understanding the world. If the universe was inherently uncertain at the quantum level, what did that mean for the pursuit of knowledge? Was science merely a tool for describing the probability of events, or could it provide us with more concrete, certain truths about reality? These questions had been explored by philosophers for centuries, but Heisenberg's work on quantum mechanics brought them to the forefront of scientific inquiry in a new and profound way. Heisenberg's uncertainty principle also raised important questions about the nature of reality itself. If particles did not have definite positions and momenta, what did that mean for our understanding of physical objects? In the classical world, objects were defined by their precise locations and velocities. However, in the quantum world, particles existed in a state of probability with multiple potential outcomes. This led to the development of the wave-particle duality theory, which posited that particles could exhibit both wave-like and particle-like properties depending on how they were observed. This wave-particle duality, along with the uncertainty principle, suggested that the very act of observation influenced the system being observed. The observer, in a sense, played a central role in determining the outcome of an experiment. This was a departure from the classical view of the observer as a passive observer of reality. Instead, the observer in the quantum world actively shaped the outcome of events. This concept of the observer effect raised deep philosophical questions about the nature of reality and the limits of human knowledge. Could we ever truly understand the universe, or was our perception always constrained by the limits of observation? Heisenberg's contributions to quantum mechanics, particularly the uncertainty principle, were groundbreaking in their own right. However, his work also led to significant philosophical and intellectual shifts. The implications of the uncertainty principle were not limited to the realm of physics. They challenged deeply held assumptions about the nature of reality, knowledge, and determinism. Heisenberg's work raised profound questions about the limits of human understanding and the role of the observer in shaping the world around us. In many ways, Heisenberg's work represented a break from the classical tradition. The classical view of the universe, as defined by figures like Newton and Laplace, saw the world as a deterministic system governed by fixed laws. In contrast, Heisenberg's quantum mechanics presented a universe that was probabilistic, uncertain, and governed by the fundamental limits of knowledge. This shift in perspective opened up new avenues for scientific and philosophical inquiry, setting the stage for future breakthroughs in the field of quantum mechanics and beyond. Heisenberg's work also laid the groundwork for future developments in quantum theory. The uncertainty principle and the probabilistic nature of quantum mechanics opened the door for new research into quantum entanglement, quantum computing, and the search for a unified theory of physics, these areas of research are at the forefront of modern physics and have the potential to revolutionize our understanding of the universe. Heisenberg's contributions to the philosophy of science are as important as his contributions to quantum mechanics. His work forced a re-evaluation of the scientific method, the role of the observer, and the limits of human knowledge. The uncertainty principle was not just a mathematical formula, it was a philosophical statement about the nature of reality itself. It suggested that the universe was not as predictable or understandable as we had once believed, and that there were limits to what we could know. Heisenberg's legacy is not just in the equations he formulated or the theories he developed, but in the way he reshaped our understanding of the universe and our place within it. His work continues to influence the way we think about reality, knowledge, and the limits of human understanding. Through his contributions to quantum mechanics and the philosophy of science, Heisenberg made an indelible mark on both fields, and his legacy continues to inspire scientific and philosophical inquiry today. In conclusion, Werner Heisenberg's contributions to quantum mechanics, particularly his development of the uncertainty principle, were transformative not just for physics but for the broader intellectual world. He challenged long-standing assumptions about determinism, knowledge, and reality itself, and his work remains a cornerstone of modern physics. Heisenberg's legacy continues to shape the way we think about the universe, and his ideas remain as relevant today as they were when he first introduced them. Through his work, Heisenberg did not just change the course of science, he changed the way we understand the very nature of existence. Heisenberg's uncertainty principle and his contributions to quantum mechanics not only reshaped the scientific understanding of the atomic world, but also gave rise to profound philosophical implications that challenge the very way we think about knowledge, reality, and the limits of human perception. The uncertainty principle, in particular, became the cornerstone of quantum theory, revolutionizing not just physics, but also the larger intellectual landscape that intersects science, philosophy, and even metaphysics. The principle asserted that the more precisely we know the position of a particle, the less precisely we can know its momentum, and vice versa. This was not a flaw of measurement or instrumentation, but an inherent feature of the quantum world, a result of the nature of particles themselves. At the heart of Heisenberg's work is a shift away from the classical Newtonian worldview that had dominated scientific thought for centuries. Classical mechanics, as proposed by Sir Isaac Newton, was based on the idea of a deterministic universe, where the future of any object could be predicted with absolute certainty given its current state. If we could know the position and velocity of an object, we could predict where it would be in the future. This deterministic model had a certain elegance and comfort, providing an understanding of the universe as an ordered, predictable system. However, as quantum mechanics emerged, particularly through the work of Heisenberg, it revealed that at the atomic and subatomic levels, the universe operates on fundamentally different principles. Heisenberg's matrix mechanics, developed in 1925, provided the first rigorous framework to describe quantum phenomena mathematically. Rather than envisioning particles as physical objects that move along predictable paths, Heisenberg's work demonstrated that the behavior of particles could only be understood in terms of probabilities, with the particle's location and momentum not being precisely determined. This shift away from deterministic laws was a sharp break from classical physics, introducing an era in which the universe at the quantum level could only be understood in terms of likelihoods and uncertainties. Heisenberg's uncertainty principle itself went beyond just the technical implications for how physicists understood quantum systems. It signaled a major philosophical shift, one that would stir deep discussions among scientists, philosophers, and even the public at large. The uncertainty principle raised the question, what can we truly know about the world? The very fabric of reality was no longer defined by fixed, measurable quantities but by probabilities. For the first time, scientists were faced with the unsettling reality that there were intrinsic limits to what could be known, at least in certain domains. This was not just a limitation of technology or measurement tools. It was a fundamental property of nature itself. The philosophical implications of the uncertainty principle went beyond just the idea of knowledge limitations in quantum physics. The principle challenged the classical notion of objective reality, the idea that the world exists independently of our observation and that it can be described with certainty, regardless of whether anyone is observing it. Under Heisenberg's principle, observation became a crucial element in defining the state of a system. The act of measurement in quantum mechanics did not simply reveal the properties of an object, it affected those properties. This shift in thinking laid the groundwork for the later development of the concept of the observer effect and contributed to the philosophical discussions around the role of consciousness in the quantum world. Heisenberg's uncertainty principle also sparked heated debates within the scientific community. One of his most notable philosophical opponents was Albert Einstein, who was deeply uncomfortable with the probabilistic nature of quantum mechanics. Einstein's famous remark, "God does not play dice with the universe," encapsulated his belief that quantum mechanics, with its inherent uncertainties, was incomplete. He argued that there must be hidden variables, undiscovered factors that could explain the apparent randomness of quantum events. Heisenberg, on the other hand, maintained that the uncertainty principle was not a mere limitation of knowledge, but an intrinsic feature of the natural world. The quantum world, Heisenberg argued, was inherently indeterminate, and it was this indeterminacy that was reflected in the uncertainty principle. This fundamental disagreement between Einstein and Heisenberg was not merely a scientific debate, but also a reflection of the deep philosophical divide between those who adhered to a deterministic worldview and those who accepted the uncertainty and probabilistic nature of quantum theory. This divide laid the foundation for some of the most famous thought experiments in the history of science, such as Schrödinger's cat, which vividly illustrated the strange and counterintuitive nature of quantum mechanics. The thought experiment involved a cat that could be both alive and dead at the same time, depending on an observation made inside a quantum system. The scenario emphasized the strange ways in which the act of measurement could influence the state of a system and questioned the nature of reality itself. Heisenberg's work on the uncertainty principle and its subsequent philosophical implications extended far beyond the confines of the scientific community. It infiltrated the broader intellectual and cultural discussions of the 20th century. In the wake of quantum mechanics, thinkers from various fields, ranging from philosophy and metaphysics to literature and art, began grappling with the challenges posed by the uncertainty principle. The very nature of truth, reality, and human knowledge had to be re-examined in light of the realization that uncertainty was an essential part of nature. This philosophical shift had a profound impact on the way the modern world approached knowledge. Furthermore, Heisenberg's influence did not stop at the theoretical level. His work had practical consequences that continue to shape the world today. Quantum mechanics, which Heisenberg helped to develop, forms the foundation of much of modern technology. Semiconductors, lasers, and magnetic resonance imaging, MRI, are all made possible by quantum mechanical principles. In addition, the burgeoning field of quantum computing, which promises to revolutionize the way we process information, is grounded in the probabilistic nature of quantum mechanics. The uncertainty principle, with its focus on the fundamental limits of knowledge, continues to play a role in guiding research and technological innovation in these areas. The uncertainty principle also contributed to the development of quantum field theory, a framework that describes how quantum particles interact with fields. This theory has been instrumental in the development of the Standard Model of particle physics, which describes the fundamental particles and forces that make up the universe. Quantum mechanics, driven by Heisenberg's uncertainty principle, has allowed scientists to explore the subatomic world with unprecedented precision, leading to discoveries such as the Higgs boson and contributing to the ongoing exploration of dark matter and dark energy. As Heisenberg's uncertainty principle became integrated into the fabric of quantum mechanics, it also laid the foundation for future theoretical advancements. The probabilistic nature of quantum mechanics led scientists to explore new ideas, such as quantum entanglement and non-locality, which suggest that particles can be instantaneously connected to each other, regardless of distance. These developments continue to challenge our understanding of space, time, and causality, pushing the boundaries of human knowledge even further. Heisenberg's work, in many ways, set the stage for the vast and exciting areas of research that are being pursued in modern physics today. As we continue to explore the mysteries of the quantum world, the legacy of Werner Heisenberg remains profoundly relevant. His uncertainty principle reshaped our understanding of the universe and has had far-reaching consequences in both the scientific and philosophical domains. In particular, Heisenberg's work remains a constant reminder of the inherent uncertainty in the world around us and the limits of human knowledge. His contributions to quantum mechanics and the philosophy of science have left an indelible mark on our understanding of the universe, offering us a new lens through which to view the fundamental questions of existence. Through his work, Heisenberg transformed our understanding of reality itself, offering a glimpse into a universe that is far stranger and more complex than we had ever imagined. In conclusion, Heisenberg's contributions to quantum mechanics were not merely scientific breakthroughs, but philosophical and intellectual shifts that continue to reverberate throughout modern thought. The uncertainty principle was the key to understanding the probabilistic nature of quantum systems, and in doing so, it fundamentally altered our view of the universe. Heisenberg's legacy is a testament to the power of scientific inquiry to challenge our most basic assumptions about the world and to push the boundaries of what we know and understand. Werner Heisenberg, a towering figure in the field of quantum mechanics, stands as one of the central architects of the modern understanding of the subatomic world. His contributions helped shape the trajectory of physics in the 20th century, fundamentally altering how we perceive the nature of reality itself. Heisenberg's work, especially his development of matrix mechanics and the formulation of the uncertainty principle, revolutionized not only the physical sciences but also the philosophy of knowledge, as it raised profound questions about the limits of human understanding and the nature of the universe. As we delve deeper into Heisenberg's contributions, three keynotes stand out: the birth of quantum mechanics and matrix mechanics, the profound implications of the uncertainty principle, and the philosophical implications for knowledge and reality. These elements not only highlight Heisenberg's scientific genius, but also underscore the dramatic shift in scientific and philosophical paradigms that he helped usher in. Heisenberg's entrance into the world of quantum mechanics came at a pivotal moment in scientific history. By the early 20th century, the classical physics that had dominated for centuries, shaped by the likes of Isaac Newton and Albert Einstein, was beginning to show cracks. Classical mechanics, with its deterministic framework, had provided a solid understanding of how large objects in the universe behave: planets, cars, even projectiles. However, this framework could not explain the strange phenomena observed at the microscopic, atomic level. The photoelectric effect, the behavior of blackbody radiation, and the discrete spectral lines emitted by atoms could not be accounted for by classical physics. The prevailing theories simply failed to explain how light and matter interacted at small scales, where quantum effects dominated. This realization led to the birth of quantum mechanics. At the center of this scientific revolution, Heisenberg emerged as a pioneering force. In 1925, while working with his colleagues, including Max Born and Pascual Jordan, Heisenberg developed matrix mechanics, a mathematical formalism that described the behavior of quantum systems. Matrix mechanics was one of the earliest forms of quantum mechanics, and it marked a departure from classical physics. Unlike classical mechanics, which treated particles as point masses moving along well-defined trajectories, matrix mechanics described particles in terms of probabilities. Rather than providing exact values for a particle's position and momentum at any given moment, matrix mechanics worked with abstract mathematical objects, matrices that represented different states of a quantum system. These matrices provided a set of probabilities that predicted how a particle would behave under various conditions, rather than predicting a precise path. The development of matrix mechanics was a significant breakthrough. It provided a mathematical framework that could describe the complex, unpredictable nature of particles at the quantum level. This departure from the certainty of classical physics was a radical shift, but it offered a better understanding of the atomic world. What made matrix mechanics even more remarkable was its ability to reproduce the results of earlier experiments, such as those concerning atomic spectra and the behavior of electrons in atoms. The success of matrix mechanics, however, was not without its challenges. The probabilistic nature of quantum mechanics was difficult for many to accept. Classical physics, with its deterministic worldview, had been the foundation of scientific thought for centuries. The shift to a probabilistic model of the universe was not only scientifically disruptive but philosophically unsettling. Yet, despite initial resistance, matrix mechanics, along with wave mechanics developed by Erwin Schrödinger, laid the groundwork for the modern theory of quantum mechanics. Matrix mechanics would have been a groundbreaking achievement on its own, but Heisenberg's formulation of the uncertainty principle in 1927 added another layer of depth to the emerging quantum theory. The uncertainty principle states that it is impossible to simultaneously measure certain pairs of physical properties of a particle, such as its position and momentum, with arbitrary precision. The more accurately one property is measured, the less accurately the other can be determined. This limitation was not due to experimental flaws or technological inadequacies, but was an inherent feature of nature. Heisenberg's uncertainty principle was a profound revelation. It suggested that at the quantum level, the universe did not operate in the precise, predictable way envisioned by classical physics. Instead of being able to measure the exact position and momentum of a particle simultaneously, quantum mechanics placed a fundamental limit on our ability to know these properties. This inherent uncertainty was not just a limitation of human knowledge, but an intrinsic feature of reality itself. The implications of the uncertainty principle were far-reaching, not only in terms of physics but also in the realm of philosophy. Classical physics had been rooted in the belief that if we could know the current state of a system, we could predict its future with perfect accuracy. This deterministic worldview, which had been championed by figures such as Isaac Newton and Albert Einstein, had served as the basis for scientific inquiry for centuries. Heisenberg's uncertainty principle shattered this notion. It suggested that, at the quantum level, the future could not be predicted with certainty because the very act of measurement altered the state of the system. This was a radical departure from the determinism of classical physics, and it raised fundamental questions about the nature of reality and the limits of human knowledge. The uncertainty principle also had philosophical implications beyond the realm of science. The idea that the act of observation could influence the state of a system challenged the classical view of the observer as a passive entity. In classical physics, the observer could measure the properties of a system without affecting the system itself. However, in quantum mechanics, the observer became an active participant in the process of measurement. The concept of the observer effect, which emerged from the uncertainty principle, suggested that the very act of observing a particle could alter its state. This raised profound questions about the nature of objective reality and whether we could ever truly know the world as it is, independent of our observations. While the uncertainty principle had profound philosophical implications, It also had far-reaching consequences for the scientific community. It marked the beginning of a new era in physics, one in which the concept of determinism was replaced by probabilistic models. The uncertainty principle was a cornerstone of quantum mechanics and provided the theoretical foundation for the development of quantum field theory, quantum electrodynamics, and the study of atomic and subatomic particles. It helped explain phenomena such as electron behavior in atoms, the stability of atoms, and the nature of light. Without the uncertainty principle, the modern understanding of atomic structure, radiation, and particle physics would not have been possible. The philosophical and scientific revolution that Heisenberg's uncertainty principle instigated was not limited to the world of physics. It also led to a broader re-evaluation of how we understand knowledge and reality. In the classical world, knowledge was something that could be obtained through observation and measurement, and once acquired, it was objective and independent of the observer. However, in the quantum world, knowledge became a much more fluid and subjective concept. The observer played a crucial role in determining the outcome of an experiment, and the very act of measurement shaped the reality that was being observed. This challenge to classical notions of knowledge and reality resonated with thinkers in many fields, from philosophy to psychology, and contributed to a broader intellectual shift that would have profound implications for the 20th century. Heisenberg's work also had important practical consequences. Quantum mechanics, with its probabilistic framework and the uncertainty principle at its core, laid the groundwork for many of the technological advancements that define the modern world. Semiconductors, lasers, nuclear energy, and medical technologies such as MRI scans all rely on the principles of quantum mechanics. The uncertainty principle, in particular, helped explain the behavior of particles in systems such as semiconductors, which are fundamental to modern electronics. The development of quantum technologies, such as quantum computing and quantum cryptography, has its roots in the work of Heisenberg and his contemporaries. These technologies promise to revolutionize fields, ranging from information technology to secure communication. Heisenberg's contributions also laid the foundation for many of the most important breakthroughs in physics in the second half of the 20th century. The development of the Standard Model of particle physics, which describes the fundamental particles and forces that make up the universe, relied on the probabilistic framework of quantum mechanics that Heisenberg helped to establish. The discovery of the Higgs boson, the study of quantum entanglement, and the search for a unified theory of everything all owe their origins to Heisenberg's work. Quantum mechanics has become the cornerstone of modern physics, and Heisenberg's contributions are an essential part of this ongoing scientific journey. In conclusion, Heisenberg's work on matrix mechanics, the uncertainty principle, and its philosophical implications laid the groundwork for much of modern physics and transformed our understanding of the universe. His contributions helped dismantle the deterministic view of the universe and introduce the concept of uncertainty at the quantum level. This shift in thinking not only reshaped the scientific landscape but also had profound philosophical and practical consequences. Through his work, Heisenberg forever changed the way we understand the world, and his legacy continues to influence the scientific and philosophical communities today. His contributions to quantum mechanics were not just groundbreaking discoveries in physics, they were revolutionary ideas that altered our perception of knowledge, reality, and the universe itself. As we continue to explore the groundbreaking work of Werner Heisenberg and his lasting impact on physics and philosophy, it is clear that his contributions were not just transformative for science, but for the very way we think about reality itself. His work on matrix mechanics, the formulation of the uncertainty principle, and his philosophical reflections on the implications of quantum mechanics fundamentally altered the trajectory of both physics and the broader intellectual landscape. The uncertainty principle, in particular, continues to be a cornerstone of quantum theory and remains central to modern scientific and philosophical discussions. In the second part of this discussion, we will delve into the lasting effects of Heisenberg's work on the field of quantum mechanics, its technological implications, and its broader philosophical consequences for understanding knowledge and reality. Heisenberg's uncertainty principle was not merely a scientific novelty, it was a radical departure from the deterministic views of the universe that had dominated physics for centuries. As we have seen, the uncertainty principle posits that it is impossible to simultaneously measure both the position and momentum of a particle with arbitrary precision. This fundamental insight implied that at the quantum level, nature itself operates according to probabilities rather than certainties. This realization disrupted the classical understanding of the universe as governed by fixed laws that could be determined and predicted with precision. In classical mechanics, if we could observe and measure enough properties of a system, we could predict its future behavior with certainty. But quantum mechanics, through Heisenberg's work, showed us that, at the atomic and subatomic levels, the future is fundamentally uncertain, governed by probabilities. This departure from determinism forced a reconsideration of the very nature of reality. Heisenberg's uncertainty principle revealed that the universe, at its most fundamental level, could not be fully known in the traditional sense. Instead of a mechanical, clockwork universe where everything is determined by a set of known laws, quantum mechanics proposed a reality where knowledge was limited and uncertainty was an inherent feature of the universe. This idea was difficult for many to accept, especially for physicists who were rooted in the classical tradition. Even Albert Einstein, one of the greatest physicists of the time, rejected the implications of Heisenberg's uncertainty principle, famously saying, "God does not play dice with the universe." Einstein's belief in a deterministic, clock-like universe stood in stark contrast to Heisenberg's probabilistic quantum reality. And this philosophical divide between Einstein and Heisenberg became one of the most famous scientific debates of the 20th century. Yet, despite the resistance, Heisenberg's uncertainty principle became a cornerstone of quantum mechanics, and its implications reached far beyond the realm of physics. As the foundation of quantum theory, it reshaped our understanding of the universe, suggesting that at its core, reality is not governed by a set of precise, measurable laws, but by probabilities and uncertainties. This shift led to a re-examination of the very nature of knowledge and the limits of human perception. If the universe could not be fully known, if there were limits to what we could measure and understand, then how could we ever claim to possess complete knowledge of the world? This question became central to the philosophy of science in the 20th century and led to profound debates about the nature of truth, observation, and reality. The uncertainty principle also had significant philosophical ramifications for the idea of objectivity. In classical physics, the observer was a passive entity, someone who measured the world without affecting it. However, in the quantum world, the observer became an active participant in the measurement process. The very act of observation altered the state of the system being measured, a concept that is encapsulated in the observer effect in quantum mechanics. This idea challenged the classical notion of objective reality, in which the world exists independently of human perception. Instead, quantum mechanics, through Heisenberg's work, suggested that reality is not fixed or objective, but is influenced by our observations and measurements. This realization raised profound philosophical questions about the nature of existence itself and the limits of human knowledge. These philosophical questions were not merely academic, they had real-world consequences. The development of quantum mechanics and the uncertainty principle also opened the door to new technologies that rely on the probabilistic nature of quantum systems. One of the most profound technological developments to arise from quantum mechanics is the field of quantum computing. Unlike classical computers, which process information as binary data, 1 second and 0 seconds. Quantum computers use quantum bits, or qubits, which can represent multiple states simultaneously. This ability to exist in multiple states at once, known as superposition, results from the very principles that Heisenberg's uncertainty principle and quantum mechanics introduced. Quantum computing has the potential to revolutionize fields such as cryptography, artificial intelligence, and complex problem solving, offering new ways to process information far more efficiently than classical computers ever could. Another area where Heisenberg's work has had a profound impact is in quantum cryptography. Quantum mechanics allows for secure communication methods based on the uncertainty principle, where the act of eavesdropping on a quantum communication channel alters the state of the system, making it impossible for an observer to intercept information without being detected. This principle forms the basis of quantum key distribution, a technology that is already being tested and deployed for secure communication networks. In these cases, the uncertainty principle is not just a theoretical concept but a practical tool that has real-world applications in creating secure digital communications. Beyond these technological advancements, Heisenberg's work on quantum mechanics and the uncertainty principle continues to shape the way physicists approach the study of the universe. Quantum mechanics has become the most successful and well-tested theory in the history of science. From predicting the behavior of electrons in atoms to explaining the interactions of fundamental particles, quantum mechanics has provided us with a remarkably accurate description of the microscopic world. Heisenberg's contributions, particularly his uncertainty principle, remain central to the study of atomic and subatomic phenomena. Without the understanding of uncertainty, much of the progress made in fields such as particle physics, quantum chemistry, and material science would not have been possible. Heisenberg's influence also extends beyond the realm of physics. His work on the uncertainty principle and quantum mechanics has influenced the development of philosophy of science, particularly in areas such as epistemology and metaphysics. Philosophers have been deeply concerned with the implications of quantum mechanics for our understanding of reality. If the universe at the quantum level is uncertain, does this mean that all of reality is uncertain? Is the classical view of a stable, objective reality a mere illusion? These questions have sparked a re-examination of the nature of existence and the limits of human knowledge. The uncertainty principle, by showing that uncertainty is a fundamental property of nature, has led to new ways of thinking about the nature of truth, knowledge, and existence. The intellectual legacy of Heisenberg's work is not limited to the fields of physics and philosophy. His ideas have influenced a wide range of disciplines, from biology to psychology, where uncertainty and probabilistic models are increasingly being applied to understand complex systems. In biology, for example, the probabilistic models of quantum mechanics have been used to understand the behavior of molecules and enzymes. In psychology, concepts from quantum mechanics, including uncertainty and indeterminacy, have been applied to theories of human cognition and decision-making. Heisenberg's work on uncertainty, therefore, has had far-reaching effects, helping to shape not just our understanding of the physical world, but also the broader intellectual landscape. In conclusion, Werner Heisenberg's contributions to quantum mechanics, particularly his development of the uncertainty principle, have had profound and lasting effects on both science and philosophy. His work marked a radical departure from the deterministic view of the universe that had dominated classical physics, introducing a new paradigm in which uncertainty and probability are fundamental features of reality. The uncertainty principle has not only reshaped our understanding of the microscopic world, but also raised profound questions about the nature of knowledge, observation, and existence. The technological advancements that have emerged from quantum mechanics, including quantum computing and quantum cryptography, are a testament to the practical applications of Heisenberg's ideas. His legacy continues to influence scientific inquiry today, and his work remains a cornerstone of modern physics, guiding both the exploration of the universe and the ongoing philosophical debate about the nature of reality. Heisenberg did not just change physics, he changed the way we think about the world. Werner Heisenberg's contributions to quantum mechanics and his formulation of the uncertainty principle have had profound and lasting effects on both the field of physics and the broader intellectual landscape. His pioneering work challenged classical notions of determinism and introduced a new understanding of the subatomic world. As we explore the keynotes of Heisenberg's legacy, we can break them down into four significant areas: the development of matrix mechanics, the uncertainty principle, the impact of his work on the philosophy of science, and his role in shaping modern quantum theory. Each of these areas highlights how Heisenberg's work has fundamentally changed how we perceive the universe and our place within it. Heisenberg's most immediate contribution was the development of matrix mechanics, a mathematical framework for quantum mechanics. In 1925, Heisenberg, along with his colleagues Max Born and Pascual Jordan, developed matrix mechanics as a way to describe atomic systems without relying on classical ideas like definite particle trajectories. Instead of focusing on the position and velocity of particles, matrix mechanics dealt with probabilities, using matrices to represent the possible states of quantum systems. This marked a significant departure from classical mechanics, which treated particles as fixed objects with well-defined positions and velocities. Matrix mechanics was revolutionary because it allowed physicists to describe atomic behavior in ways that were consistent with experimental observations, particularly the behavior of electrons in atoms. It was a bold new approach to understanding the microworld, and while it was initially difficult to grasp, it proved to be a successful framework that later became a foundational aspect of quantum mechanics. Following his development of matrix mechanics, Heisenberg introduced the uncertainty principle in 1927, which became one of the most important and well-known concepts in quantum mechanics. The uncertainty principle states that it is impossible to simultaneously measure both the position and momentum of a particle with arbitrary precision. The more precisely one property is measured, the less precisely the other can be known. This was not a limitation of experimental tools, but an inherent feature of nature itself. The uncertainty principle suggested that the universe, at the quantum level, is inherently probabilistic rather than deterministic. In classical physics, one could predict the future of a system with great precision if enough information about its current state was known. However, Heisenberg's uncertainty principle challenged this view, implying that the very act of measuring a particle altered its state. This fundamental uncertainty disrupted the classical notion that the universe was governed by fixed, predictable laws, and it opened the door to a new understanding of reality. Heisenberg's work also had profound philosophical implications. Classical physics had been rooted in the idea of a deterministic universe, where if we knew the initial conditions of a system, we could predict its future behavior with certainty. However, Heisenberg's uncertainty principle suggested that at the quantum level, the future was not strictly predictable. This shift in understanding raised deep philosophical questions about the nature of reality and knowledge. If there were limits to what we could know about the world, how could we claim to understand the universe in its entirety? These questions echoed through the intellectual landscape of the 20th century, leading to a re-evaluation of scientific epistemology and the limits of human knowledge. For Heisenberg, the uncertainty principle was not just a scientific discovery, it was a profound statement about the nature of the world. The realization that the universe was governed by uncertainty had far-reaching implications for how scientists, philosophers, and even the general public viewed the world around them. Finally, Heisenberg's contributions played a crucial role in shaping the future of quantum theory and modern physics. His development of matrix mechanics laid the foundation for the broader quantum mechanical framework, which eventually led to the formulation of quantum field theory, quantum electrodynamics, and the study of quantum particles. The probabilistic nature of quantum mechanics, underscored by the uncertainty principle, also played a pivotal role in shaping the development of quantum computing, which is poised to revolutionize fields like cryptography and artificial intelligence. Moreover, Heisenberg's work influenced the development of modern particle physics, leading to the exploration of concepts like quantum entanglement and the search for a unified theory of everything. Heisenberg's ideas have been instrumental in pushing the boundaries of knowledge and have led to major technological advancements that are now deeply embedded in our daily lives. Through these four keynotes: matrix mechanics, the uncertainty principle, philosophical implications, and the development of modern quantum theory, Heisenberg's contributions have left an indelible mark on both the scientific and philosophical communities. His work revolutionized our understanding of the subatomic world and transformed the way we think about reality itself. Heisenberg's legacy is not just in the equations he formulated or the theoretical frameworks he developed, but in the way his work continues to shape the direction of modern physics, technology, and intellectual thought. His contributions have helped us unlock the mysteries of the quantum world and have forever altered the trajectory of human understanding. Werner Heisenberg, one of the founding fathers of quantum mechanics, played a pivotal role in reshaping our understanding of the universe. His work introduced a fundamental shift from classical physics, breaking the age-old assumptions that had governed scientific thought for centuries. Heisenberg's contributions spanned several crucial areas: the development of matrix mechanics, the introduction of the uncertainty principle, his collaboration with other great minds like Niels Bohr, his philosophical reflections on the limits of human knowledge, and the practical applications of quantum mechanics that followed. These five keynotes encapsulate Heisenberg's profound impact on physics and philosophy, each offering a unique perspective on how he changed the way we view the world. Heisenberg's development of matrix mechanics in 1925 was one of his most important contributions to quantum mechanics. At a time when classical physics was still deeply ingrained in scientific thinking, Heisenberg and his colleagues, Max Born and Pascual Jordan, created a mathematical framework that allowed the behavior of atomic and subatomic particles to be described without relying on classical concepts such as particle trajectories. Instead of treating particles as objects with well-defined positions and velocities, matrix mechanics used matrices to represent quantum states. These matrices allowed for the calculation of probabilities, not certainties, making it a radical departure from classical physics. The success of matrix mechanics in explaining phenomena that classical mechanics could not account for, such as the behavior of electrons in atoms, confirmed its validity. This marked a critical turning point in the history of physics, as it provided a new approach to understanding the microscopic world, one that was based on probabilities rather than fixed, deterministic outcomes. In 1927, Heisenberg introduced the uncertainty principle, a concept that would become the cornerstone of quantum mechanics. This principle states that there is a fundamental limit to how precisely certain pairs of properties of a particle, such as position and momentum, can be measured simultaneously. The more precisely one property is measured, the less precisely the other can be known. The uncertainty principle was not just a limitation of measurement instruments or techniques, but an intrinsic feature of nature itself. Heisenberg's discovery shattered the classical view that the universe operated in a predictable and deterministic manner. If classical physics had taught us that with enough information we could predict the future with certainty, the uncertainty principle introduced a radical new understanding. At the quantum level, uncertainty is built into the fabric of nature, and some things are inherently unknowable. This principle would go on to redefine our approach to understanding the universe, introducing the concept of probabilistic rather than deterministic laws of nature. Heisenberg's work was not conducted in isolation. His collaborations with other leading physicists of the time, particularly Niels Bohr, played a critical role in shaping the development of quantum mechanics. The debates and intellectual exchanges between Heisenberg and Bohr especially over the interpretation of quantum mechanics, were key moments in the history of physics. While Bohr supported the probabilistic nature of quantum mechanics and the role of observation in shaping reality, Heisenberg's uncertainty principle introduced a more radical view of the limits of human knowledge. Their discussions deepened the understanding of quantum theory and helped shape the philosophical discussions surrounding the nature of reality itself. These collaborations between Heisenberg and other great minds such as Max Born, Albert Einstein, and Erwin Schrödinger helped lay the foundation for quantum mechanics as we know it today. Despite their differing views, these intellectual exchanges catalyzed the development of a new scientific paradigm. The philosophical implications of Heisenberg's work extended far beyond the realm of physics. The uncertainty principle, in particular, raised profound questions about the nature of reality and the limits of human knowledge. In classical physics, the universe was thought to be an objective, observable reality, governed by laws that could be determined and understood. However, Heisenberg's work suggested that, at the quantum level, the universe is not fixed or fully knowable. The uncertainty principle revealed that the very act of observation affects the system being observed, which challenged the idea of an objective reality that exists independently of the observer. This marked a shift in the philosophy of science, prompting thinkers to reconsider the nature of knowledge and the role of perception in shaping our understanding of the world. Heisenberg's work was not just about explaining the behavior of particles. It was about redefining the very concept of reality itself, suggesting that uncertainty and indeterminacy are fundamental aspects of the universe. Finally, Heisenberg's work laid the groundwork for numerous technological advancements. While his contributions to theoretical physics are often the focus, the practical applications of quantum mechanics, which Heisenberg helped to pioneer, have had a profound impact on technology. From semiconductors to lasers, MRI machines, and the burgeoning field of quantum computing, the principles of quantum mechanics, especially the uncertainty principle, have found applications that have revolutionized modern technology. Quantum computing, for example, relies on the probabilistic nature of quantum particles, exploiting their ability to exist in multiple states simultaneously. This has the potential to vastly outperform classical computers in certain tasks, such as solving complex problems in chemistry, cryptography, and artificial intelligence. Heisenberg's contributions, therefore, not only reshaped our theoretical understanding of the universe, but also laid the foundation for technologies that are now indispensable in modern life. In conclusion, the 5 keynotes of Heisenberg's work, his development of matrix mechanics, the formulation of the uncertainty principle, his collaborations with other great physicists, the philosophical implications of his work, and the technological applications that followed, illustrate the profound and lasting impact he had on both the scientific world and broader intellectual thought. Heisenberg's contributions went beyond the equations he formulated or the theories he developed. They fundamentally reshaped the way we think about the universe. His work opened up new avenues for scientific exploration, challenged our assumptions about knowledge and reality, and paved the way for technologies that have transformed modern life. Heisenberg's legacy is not only in the theories he helped to establish, but also in the way his ideas continue to influence the course of physics and philosophy today. Through his work, Heisenberg didn't just change physics, he changed the way we understand the very fabric of existence. Werner Heisenberg, one of the key figures in the development of quantum mechanics, revolutionized the way we understand the subatomic world. His work on the uncertainty principle and his development of matrix mechanics are widely regarded as some of the most important contributions in modern physics. However, Heisenberg's legacy extends beyond these discoveries, influencing not only the scientific community but also the philosophical and technological landscapes of the 20th century. 6 keynotes can be highlighted to explain Heisenberg's monumental impact: the rise of quantum mechanics, the introduction of matrix mechanics, the uncertainty principle, The implications for determinism, Heisenberg's philosophical reflections on science, and the lasting technological contributions of quantum theory. The rise of quantum mechanics in the early 20th century marked a paradigm shift in the understanding of the physical world. Classical mechanics, which had been the cornerstone of physics since the time of Newton, was no longer able to explain the strange behaviors observed at the atomic and subatomic levels. Phenomena such as the photoelectric effect, blackbody radiation, and the stability of atoms could not be explained by classical physics. The development of quantum theory emerged as a response to these inconsistencies. Heisenberg's early work, especially his development of matrix mechanics, was a crucial piece of this puzzle. It provided the mathematical framework necessary to describe the behavior of particles in quantum systems. This marked the beginning of a new era in physics, one that would go on to radically change our understanding of matter and energy. Matrix mechanics, developed by Heisenberg in collaboration with Max Born and Pascual Jordan in 1925, was one of the first successful formulations of quantum mechanics. Unlike classical mechanics, which treats particles as objects moving along well-defined trajectories, matrix mechanics describe particles in terms of probabilities and states. In matrix mechanics, physical quantities such as position, momentum, and energy were represented by matrices, mathematical structures that described possible states of a system. This approach was a departure from classical physics, where particles were thought to have specific, measurable properties. Instead, matrix mechanics focused on the probabilities of these properties, making it a key early development in quantum theory. Despite being initially difficult to understand, matrix mechanics became a cornerstone of quantum mechanics and laid the foundation for future work in the field. In 1927, Heisenberg introduced the uncertainty principle, one of the most famous concepts in quantum mechanics. The uncertainty principle asserts that it is impossible to measure both the position and momentum of a particle with absolute precision at the same time. The more accurately one of these properties is measured, the less accurately the other can be known. This was not a limitation of our measuring instruments or experimental techniques, but a fundamental property of nature. The uncertainty principle challenged the classical view of the universe, where precise measurements of physical quantities were assumed to be possible. Instead, Heisenberg's principle proposed that at the quantum level, particles do not have well-defined positions and velocities at all times. Instead, their behavior is inherently probabilistic. This principle had profound implications for the study of physics, suggesting that uncertainty and indeterminacy were not merely byproducts of our inability to measure, but intrinsic features of the physical world. The uncertainty principle also had significant implications for the classical idea of determinism. In classical physics, the universe was governed by deterministic laws. If we knew the current state of a system, we could predict its future behavior with certainty. However, the uncertainty principle suggested that at the quantum level, this kind of prediction was impossible. The very act of measurement could alter the state of a system, and there was no way to simultaneously determine certain properties with perfect precision. This was a radical departure from the deterministic worldview that had dominated science for centuries. The probabilistic nature of quantum mechanics, underscored by the uncertainty principle, made it clear that the universe was not entirely predictable. Instead of a world where everything was determined by fixed laws, the quantum world was governed by uncertainty and probability. This shift in perspective had profound philosophical implications, raising questions about the nature of reality and whether a truly deterministic universe could ever be realized. Heisenberg's work on the uncertainty principle also prompted deep philosophical reflections on the nature of science itself. If the universe could not be known with complete certainty, what did that mean for scientific knowledge? Heisenberg's discovery pointed to the limits of human understanding and highlighted the fact that certain aspects of reality might forever remain beyond our grasp. This raised questions about the relationship between observation and reality, whether the act of measuring something could ever reveal its true nature. This philosophical challenge was not just about the limitations of quantum mechanics but also about the nature of scientific knowledge. Heisenberg's work emphasized that science is not about uncovering an objective, unchanging reality but rather about working within the limits of what can be known and measured. This insight would influence not only physics but also the broader philosophy of science in the 20th century, particularly in debates about the nature of truth and the role of the observer. Finally, Heisenberg's work laid the groundwork for a host of technological innovations that have transformed modern life. Quantum mechanics, built upon Heisenberg's insights, has been essential in the development of technologies such as semiconductors, lasers, and magnetic resonance imaging, MRI. The uncertainty principle and the probabilistic nature of quantum mechanics were integral to the development of these technologies, which have become fundamental to fields ranging from electronics to medicine. More recently, quantum mechanics has driven the development of quantum computing, a field that holds the potential to revolutionize information processing. Quantum computers, which leverage the probabilistic nature of quantum systems, are poised to tackle problems that classical computers cannot, particularly in fields like cryptography, optimization, and artificial intelligence. These advancements demonstrate that Heisenberg's theoretical contributions continue to have a profound impact on technological innovation, shaping the tools and systems that define the modern world. In conclusion, Heisenberg's contributions to quantum mechanics and his broader philosophical reflections have had a lasting impact on both the scientific and technological landscapes. His development of matrix mechanics, the introduction of the uncertainty principle, and his challenge to the deterministic worldview of classical physics opened up new avenues of exploration in physics. The implications of his work extended far beyond the realm of science, raising profound questions about the nature of knowledge and reality. Furthermore, Heisenberg's ideas continue to influence the development of modern technologies, from semiconductors to quantum computing, which rely on the principles of quantum mechanics that he helped to establish. Heisenberg's legacy is a testament to the power of scientific inquiry to reshape our understanding of the universe and to create new technologies that impact every aspect of modern life. His work did not merely change physics, it changed the way we see the world. Werner Heisenberg, a central figure in the development of quantum mechanics, profoundly impacted both physics and philosophy. His groundbreaking work reshaped our understanding of the atomic and subatomic worlds, challenging centuries-old beliefs about determinism, knowledge, and reality. 7 keynotes illustrate the depth of his contributions: the emergence of quantum mechanics, the formulation of matrix mechanics, the creation of the uncertainty principle, the philosophical shift regarding determinism, the observer effect in quantum mechanics, Heisenberg's role in the development of modern physics, and the technological applications of quantum mechanics. Quantum mechanics emerged in the early 20th century as a response to the limitations of classical physics. Classical physics, based on the laws of Newtonian mechanics, worked well for large-scale objects like planets and everyday phenomena. However, it failed to explain behavior at the atomic and subatomic levels. Phenomena such as the photoelectric effect and the discrete nature of atomic spectra posed challenges that classical theories could not resolve. This led to the birth of quantum theory, a new framework for understanding the behavior of matter at microscopic scales. Heisenberg's contributions were instrumental in this revolution, offering new ways to describe the behavior of particles that classical physics could not account for. His development of matrix mechanics in 1925 was a significant step forward in this new scientific paradigm. Matrix mechanics, developed by Heisenberg in collaboration with Max Born and Pascual Jordan, was one of the first successful formulations of quantum mechanics. Unlike classical mechanics, which treated particles as having definite positions and velocities, matrix mechanics described particles in terms of probabilities. Heisenberg's approach used mathematical matrices to represent the different possible states of a quantum system. This allowed scientists to calculate the likelihood of a particle being in a particular state, rather than predicting its exact position or momentum. Matrix mechanics marked a departure from the deterministic worldview of classical physics and laid the groundwork for future developments in quantum mechanics. Though initially difficult to grasp, matrix mechanics proved to be a powerful tool for understanding the behavior of quantum systems. The uncertainty principle, introduced by Heisenberg in 1927, became one of the most famous and influential concepts in quantum mechanics. It asserts that it is impossible to simultaneously measure both the position and momentum of a particle with absolute precision. The more accurately one property is measured, the less accurately the other can be known. This principle was not a limitation of experimental techniques, but an inherent feature of the quantum world. The uncertainty principle challenged the classical view of a predictable universe, where all properties could be measured and known. In the quantum world, Heisenberg showed, uncertainty was not just a theoretical concept, but a fundamental aspect of nature itself. The principle suggested that, at the subatomic level, particles do not exist in fixed, deterministic states, but in a realm of probabilities. The uncertainty principle had far-reaching implications for the classical idea of determinism. Classical physics, from Newtonian mechanics to Einstein's theories of relativity, was built on the idea that the universe was governed by fixed, predictable laws. If we knew the initial conditions of a system, we could predict its future behavior with certainty. Heisenberg's work, however, showed that at the quantum level, the future was not fully predictable. The act of measurement itself could alter the state of a system, and the uncertainty principle demonstrated that some aspects of reality are simply unknowable. This shift from a deterministic to a probabilistic worldview not only revolutionized physics, but also provoked deep philosophical questions about the nature of reality, free will, and knowledge. One of the most fascinating aspects of quantum mechanics, influenced by Heisenberg's uncertainty principle, is the role of the observer. In classical physics, the observer was considered a passive participant in experiments. The laws of nature were thought to exist independently of observation. However, quantum mechanics introduced the idea that the observer plays an active role in shaping the outcome of an experiment. Heisenberg's uncertainty principle suggested that the very act of measurement could disturb the system being measured, making it impossible to observe certain properties without affecting them. This led to the concept of the observer effect, which challenges the classical notion of objective reality and raises questions about the limits of human knowledge. Heisenberg's contributions also played a crucial role in shaping the future of quantum theory and modern physics. He was part of the intellectual community that developed quantum mechanics into a comprehensive theory, building upon the work of other pioneers like Niels Bohr and Albert Einstein. His work on matrix mechanics and the uncertainty principle was foundational for the development of quantum field theory, which describes how quantum particles interact with fields. This theory underpins much of modern particle physics, including the Standard Model, which describes the fundamental particles and forces that make up the universe. Heisenberg's influence is seen not only in the theories he developed, but also in his role as a teacher and mentor to the next generation of physicists. The technological applications of quantum mechanics, which Heisenberg helped to establish, have had a transformative impact on the modern world. Quantum mechanics has been fundamental in the development of technologies such as semiconductors, lasers, and magnetic resonance imaging, MRI. These innovations have revolutionized industries ranging from electronics to medicine. More recently, quantum mechanics has opened the door to the emerging field of quantum computing. Quantum computers, which exploit the probabilistic nature of quantum systems, hold the potential to solve problems that classical computers cannot. These technologies rely on the principles of quantum mechanics that Heisenberg and his colleagues helped to establish, and they continue to shape the future of technology. In conclusion, Heisenberg's work was central to the development of quantum mechanics and the understanding of the atomic and subatomic world. Through his work on matrix mechanics, the uncertainty principle, and his philosophical reflections on the nature of reality, Heisenberg introduced a paradigm shift in how we understand the universe. His contributions not only revolutionized physics but also reshaped the philosophical discourse around knowledge, determinism, and the limits of human understanding. The lasting impact of Heisenberg's work is evident in the development of modern physics, the technological advances that have followed, and the ongoing philosophical debates that continue to shape the intellectual landscape today. Heisenberg's legacy is a testament to the power of science to transform our view of reality and to challenge the assumptions that have governed human thought for centuries.